Welcome. In this video, we look at section 1.3, the basics of propositional logic. Three big ideas. We will look at propositional logic, truth tables, and a neat puzzle based on liars and truth tellers. All right, let's begin. Propositional logic. So a proposition is a statement that is either true or false. So, for example, here are two propositions. Sue is an English major and Sue is a junior. In arithmetic, we often use variables to represent numbers. Well, in logic, we use variables to represent propositions. And we can combine propositions in the same way that we combine numbers. In arithmetic, we have addition and multiplication. With logic, we have connectives that tell us and, or, and not. So I can make statements like, Sue is an English major and Sue is a junior. So in other words, Sue is a junior English major. We might say that more naturally. The second one, Sue is an English major or she is a junior. Sue is not an English major. All right, how about this last one? How about Sue is an English major and a junior, or it is not the case that Sue is an English major or not a junior. And I don't know that I can really untangle that whole expression and really get a sense of what it means, but at least we can say it out loud. Well, how about this? Here are several statements kind of written in natural language. Let's see how we turn these into logical statements using propositions and connectives. This follows the example from before, with E being Sue is an English major and J representing Sue is a junior. So number one says Sue is a junior English major. Well, she is both a junior and she is an English major, so this will become J and E. She is both of those. All right, at this point, I want you to pause the video and try the remaining problems and then start up again when you think you have your solutions. All right, go to it. So, number two, Sue is either an English major or she is a junior. That's just one or the other. We got the or sign in there. 3, Sue is a junior, but she is not an English major. This is interesting. In English, we use the word but to express the idea that there are contrasting ideas. Logically, the word but is really the same as the word and. It would sound a little weird to say it, but it is the same truth. Sue is a junior and she is not an English major. So in natural language, we use the word but logically that really means the same thing as and. Number 4, Sue is neither an English major nor a junior. A couple ways we might express this: not a junior and not an English major. Or you might express this as, it is not the case that she is a junior or an English major, right? Because it's that neither in there that's telling us she can't be one or the other. And lastly, number 5, Sue is either an English major or a junior, but, and, she is not a junior English major. So what does that look like? There we go. Let's move on. Let's look at truth tables. Truth tables give us a nice way of organizing our thoughts about propositions and determining whether some big expression is true or false. Well, the most simple way of connecting things is just with and or. So let's say I have a proposition P and a proposition Q. The truthhood and or falsity of P and Q can exist in 4 ways. Either they're both true, P is true, Q is false, P is false, Q is true, or P is false and Q is false. Those are the only 4 possibilities that I can have with these two propositions. So how about the and? The and is saying P is true and Q is true. So which of these 4 here below have the situation in which P is true and Q is true? Well, only the first one. In the first case, it's P is true and Q is true. In the second case, no, they're not both true. Third case, no, they're not both true. Fourth case, no, they're not both true. So this is the truth table for the and connective. How about the or connective? True and true is either one of those true? Yes. True and false is either one of those true? Yes. False and true is either one of those true? Yes. False and false is at least one of those true? No. So our column for the or becomes true, 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 false. And then finally, the negation, the not P. At this point, all we do is look at the P column. The and the or are binary operators. They take two propositions to return a value. The negation is a unary operator. It only needs one. And so when I negate the P column, I get false, false, true, true. So that is the basis for how we combine propositions together. So we can make more complicated things. We can make compound statements out of simple statements. For example, let's find the truth table for the statement not P or Q. Well, I make it simpler by starting with the inside. So first I figure out P or Q. All right, well, P or Q, that's going to be true, 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 false. And then I can negate that. I'm just negating the column that came before it. So false, 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 true. And that is it. There is the truth table for this logical proposition. All right. Here's a practice one for you to try. Take a moment and see if you can come up with the truth table for this proposition. All right, here's the answer. So I will negate my P, false, false, true, true. I will negate the Q column, false, true, false, true. And now I'm going to AND those two columns together. Are they both true? No, they are not. No, they are not. No, they are not. Ah, yes, it is. So there is the truth table for that statement. So when two statements have exactly the same truth table, we say that the two statements are logically equivalent. And we use the three lines to say equivalent. So in fact, if you look at those past two examples, we proved number one of De Morgan's laws. They both had the exact same truth table. Not P or Q is logically equivalent to not P and not Q. So we proved this by the truth table. There's another one of De Morgan's laws that says not the quantity P and Q is equivalent to not P or not Q. De Morgan's laws are cool when you think about it because it's like a distributive property for negation. It tells us how to distribute negation. I can distribute negation over an or, but when I do that, the or turns into an and. And I can distribute negation over an and, but when I do that, the and turns into an or. Kind of cool. All right, two special kinds of propositions. A tautology is a proposition that is always true. A contradiction is a proposition that is always false. Suppose I have a proposition P, and then I can also figure out not P. Look at this proposition, P or not P. P or not P. So is one of those true? Yes. P or not P, is one of those true? Yes. So this proposition, P or not P, that is a tautology. Can you come up with a contradiction? Right, maybe P and not P? Is it possible that a statement can be true and not true at the same time? P and not P. So when are they both true? True, oh, no, they're not both true there, so false there. P and not, no, P isn't true there, so that's false. And look at that, I have a contradiction in the right-hand column. So this statement, P and not P, that is a contradiction. All right. Consider the order of operations. The logic has an order of operations just in the same way that arithmetic has an order of operations, and behaves a lot like multiplication. And or behaves a lot like addition. And in arithmetic, we know that multiplication takes precedence over addition. You do your multiplication first and then addition. So same thing in logic. We do the ands first before we do the or. So if you see a statement, P or Q and R, in your mind, you really interpret it this way. You do the and first, Q and R, and then you OR that with the P. Suppose that you are out at a fancy dinner, you finish your dinner, and the waiter comes up to you and says, I see you're finished with your meal. Perhaps you would like some coffee and cake or pie. And most people will think, let's see, I could have coffee and I could have cake or pie. But of course, the logician is going to think, I want coffee and cake, or I want pie. This is just kind of a little bit of a warning, because sometimes how we think about the ands and ors in natural language isn't exactly how ands and ors work in logic and mathematics. In the realm of logic and mathematics, it really is the case that and always takes precedence before the or. Finally, there is one other thing, that the negation even takes precedence over the and. So if I have a statement like not P and, not capital A, and Q, I really interpret this, that is logically equivalent to not P and Q this way. The parentheses aren't needed, but in general, use parentheses for clarity. They will just help with readability. And this brings us to our third part, liars and truth tellers. These puzzles are based off of the work of a logician named Raymond Smullyan. He wrote several books of these logic riddles, and they take place on something called Smullyan's Island. There's an island, and the people on this island fall into two categories. Truth tellers, they always tell the truth, and the other people are liars. They always lie, but you can't tell them apart. And so, listening to what they say, you have to try to determine which person is a truth teller and which person is a liar. So here's an example. Suppose you go to this island, you see two people, A and B. Person A says, exactly one of us is lying. Person B says, at least one of us is telling the truth. Can you figure out which of these are truth tellers and which of these are liars? Maybe take a second to see if you can figure that out before we reveal the answer. So we can attack a problem like this, a riddle like this, with truth tables. And so here's how we might do it. I'm going to make a truth table that consists of the four possibilities that of what these people could be. So A is a truth teller, that's either true or false, and B is a truth teller, that's either true or false. So basically, scenario 1 is the situation in which A is a truth teller and B is a truth teller. Scenario 2 is the situation where A is a truth teller, B is a liar. Scenario 3, A is a liar, B is a truth teller. And scenario 4, where A is a liar and B is a liar. So which of these is the correct scenario? Now what we do is we examine their claims. What are they actually saying? Is what they say true or false? So let's examine A's claim. I'm going to focus. A says exactly one of us is lying. And let's fill in this column. Well, in scenario 1, is exactly one of them lying? No. A's claim is false. In scenario 2, A's claim is true. Scenario 3, it's true. And in scenario 4, A's claim is false. How about the rightmost column? What about B's claim? Is B saying something that is true or false? B says at least one of us is telling the truth. Okay, well, that's true there, and next one, yeah, that's true, and the third one's true, and the last one is false. All right, well, believe it or not, at this point, you have all the information to determine whether A is a liar or a truth teller, and whether B is a liar or a truth teller. Can you see it based off of this table? Maybe pause and think about it for a second. And the way you see it is, you look at where there's a match. You can't have A being a truth teller, but A saying something false. So whether A is a truth teller or a liar has to match A's statement. Oh, so this next one, this scenario 2 is a possibility where A is a truth teller and A says something true. But we run into a problem with B. In scenario 2, B is a liar, but B's claim is true. So that can't be the case either. The only place where they match up is in the fourth scenario. A is a liar and A says something false. and B is a liar, and B says something false also. So there's the match, and now we know which is the case. Absolutely, we've determined scenario 4, they are both liars. All right, here's one more example. See if you can figure this out. You really do pause the video, work through this thing, and see if you can figure out what kind of people A and B are. A says we are both telling the truth. B says A is a liar. Go to it. All right, I will work this out. So A's claim, true, false, false, false. B's claim, false, false, true, true. And where's the match? It looks like scenario 3. So it turns out that A is a liar and B is a truth teller. All right, those are the big ideas for section 1.3.